Okay, so this is problem 8.16, and in this problem we have a 100 nanofarad cap in parallel with a 2.5 Henry inductor and a resistor. We don't know the value of the resistor yet. We have initial voltage of -15 and initial current through the inductor of -5 milliamps. And we need to find the value of the resistor and the resistor has been adjusted for a critically damped response. We need to find voltage, a general equation for the voltage, the actual value of the voltage when the current through the capacitor has run out is at 0, and the amount of energy that's initially stored in this circuit that is still left when the current in the capacitor is 0. Okay, so let's start. We know that the resistor is a potentiometer that's been adjusted for a critically damped response. So that means alpha naught is equal to omega naught, and that's 1 over root LC is equal to 1 over 2 RC. That means R is equal to root LC over RC, 2C. So put these values in your calculator. And you should come up with a value of 2,500. Okay. Part B. So in Part B, we know that we have a critically damped response, which means then that we know all of our equations, or the general format of our general equation and the coefficients for it. So for critically damped, we have B of t is equal to D1 plus D1t, should be D1t, yes. D1t plus D2 e to the negative alpha t. Coefficient equations are D2 is equal to V of 0, and D1, dV dt, alpha D2. So we need to find alpha because that's the easier thing to find. So alpha is 1 over 2 RC is 1 times 100 nanos times 2,500. Put that into your calculator. You should come up with a value of 2,000. Okay, we need that for the general equation. D2 is the voltage at time 0, which is -2, -15. So we have this piece right here. This is -15. We have this piece also. This is -2,000 T. Now we need to find D1, and that's, of course, more involved. So D1, I'm going to write it up here, since I don't have board space. D1 then is equal to, if I solve for D1, it's dV dt plus alpha D2. Now, dV dt, we know, is IC over C. Okay, so we need to find IC, and we'll do that by using KCL and saying, well, IC is negative IL minus IR. Well, IR, we just found the value of the resistance, so that's going to be -15 over 2,500. So, and we were given IL, so that becomes negative and a negative is positive, 5 milliamps, plus negative and a negative is a positive again, so plus 15 over 2,500 milliamps, all of that over 100 nanofarads. When you put that into your computer or your calculator, you will come up with dVdt value of, I see over C, H2, 110 kilovolts per second. So now we have the dVdt of 110 kilovolts. We can put that back into this formula. That's 110 plus 2,000 times alpha D2 negative 15. And when you do that, that will give you a value of 80,000. Okay, so now we have everything that we need for the general equation. The general equation is going to look like this. We have D1T. D1 is 80,000 T minus D2, which is 15, e to the negative alpha, which is negative 2,000 T volts. And that is the general equation. Part 3. So part C. So in part C, we want to know what is the voltage at the point where the capacitor, current through the capacitor is equal to 0. So, well, we know that V of T, we just solved that. So we need to find out the time when this runs out. And what do we know about capacitor, the capacitor current? We know that IC is equal to C dV dt. So what can we say about IC? Well, it's either 0 when the capacitance is 0, not interesting or important, trivial, or more importantly, it's 0 when dV dt is 0. So when that's 0, the non-trivial case is when dV dt is 0. So therefore, what do we have to do? Well, we have to find the point where dV dt is 0, which means we have to differentiate the V of t. So we take the d dt of, multiply that through. So we have 80,000 T e to the negative 2,000 T minus 15 e to the negative 2,000 T. So we have to use a product rule here. And that's going to equal, I'm going to factor out the 80,000, and I'm going to take the derivative of the inside. It's going to be fixed to T times negative 2,000 e to the negative 2,000 T. Second part of this derivative is e to the negative 2,000 T times the derivative of T, which is just 1. That's this first term. The second term, the negative 15, is going to be minus 15 times negative 2,000 e to the negative 2,000 T. Okay, so that's the whole derivative. Now we distribute the 80,000 through, and we get 80 times negative 2,000 is going to give you a really big number. It's going to give you negative 160 times 10 to the 6 T e to the negative 2,000 T. And then the second term is going to be 80,000 T, and that's going to combine with this term here. And that's going to give you 110 when you actually do the 80,000 plus 15 times negative 15 times negative 15 is another 80,000. Okay, 30,000. I can't do that in my head. So it'll give you 110 over here. So that's going to be plus 110,000 e to the negative 2,000 t. Okay, now we have something that we can solve for 0. Set this equal to 0, because that's what we're looking for, is when is dV dt equal to 0, because when dV dt is equal to 0, then IC is 0, and that's what we're interested in. So when we factor out the e to the negative 2000 t, what's left inside is negative 160 times 10 to the 6 t plus 110,000. Okay, this will never be 0. The only time this equation is 0 is when this is 0. So therefore, t, move it up here. So we set this part to 0, and you have negative 160 times 10 to the 6t plus 110,000 is equal to 0. So therefore, t is 110,000 times 160 times 10 to the 6. When you put that into your computer, you will come up with that dV/dt, or the current runs out, is 0 through the capacitor at 687.5 microseconds. Okay, now that we know that time, we can plug the time back into the voltage equation to get the value of the voltage at the time the capacitor current runs out. So that's just going to be V of 687.5 micros. That's 80,000 times 687.5 micros minus 15 times e to the negative 2,000 times 687.5 micros. Okay, when you put that into your calculator, you should come up with a value of 10.1136 volts. Okay, we have the voltage that of the time when the capacitor current is 0. Now, what is the amount of energy that is left at that time? Well, in order to know that, we have to know what is the initial amount of energy. And energy, omega, is going to be the sum of the energy in the capacitor plus the energy in the inductor. So omega total is equal to omega c plus omega L. And what is that? That's 1/2 CV squared plus 1/2 Li squared. Okay? So let's find the total energy at the beginning of the circuit first. This is 1/2. Oh, I should put this here. This is 10.1136 volts. We need that to find this information. So in the beginning, we have 100 nanos times negative 15 squared plus 1/2 2.5 times negative 5 millis squared. Put that into your calculator, being very careful to get the units correct, like make sure you put in 0.005 and 10 to the negative 9 and such. And you should come up with a value here of 42.5 microjoules. That's at the beginning of the circuit. That's the energy that is stored. So let's put that here. Omega naught is equal to, at the beginning of the circuit, is 42.5 microjoules. So now, what's the energy that's still available at 0.625 microseconds? Well, we know at 6.625 microseconds, we have 10.136 volts. So energy at 687.5 micros is equal to 1/2 100 nanos times 10.1136 squared plus 1/2 2.5 henries times, well, what's the new current in the inductor now? We use KCL for that. And because capacitor current is 0, inductor current and resistor current must be the same by KCL. Therefore, IL is equal to IR, which is equal to the new voltage, V over R, which is what, 10.1136 over 2500. Square that and put that into your calculator. You should come up with a value of 25.571 microjoules. That is still left at 687.5 microseconds. That means the percentage of energy left is 25.571 over 42.5, and that should give you 60.17% of the stored energy is left. 60.17%. That's a wrap.